Chapter 14 is about string algorithms. Algorithms related to the string. All right, let's keep going. String in C++ programming is a sequence of characters. It's a sequence of characters, like an array of characters. String is so widely used in C++ that they have their own class, string class or C-string, which contains a number of methods to create and manipulate strings. Concatenate, something like that, search or find. Okay. A string is an object. A string is an object. And if it's not initialized, then it will point to null. It contains a null. Okay. We can initialize string by using a string literal, which is a text inside two double inverted commas or quotation marks, or we can initialize string using one of many constructors provided by string class, or we can use the constructors. In this chapter, we will look into implementation of some of the constructors and methods of string class, all right, that are most frequently used and which are used in this chapter. If string is just declared and not initialized, then it will point to null just like any other object in C++. So if we say, in an empty program, if we say std : string and we give it a name str, of course we need to include the string header file first. And of course, if we do not use using namespace std, then we need to put std : all right. So this is just contains a null because it's not initialized. Otherwise, if we initialize it, if we create another variable and give it a name, then it will contain whatever in the quotation marks. All right. The most easiest way to create a string is by string literal under double inverted commas. I think this is inverted because here it says double inverted, right? Just like here. So just a typing mistake, okay? Let's keep going. Another important method of creating string is by using string constructor that takes an array of characters as an argument, and this is an array. And if it's of type of character, array of characters, and here is the whatever inside, and it should always contain at the end of a string this \0, this thing. Of course, each character is written with a single quote, not double quotation marks, a single quotation mark, okay? Yeah, just like that. The string is like this, and what's inside it is this array. So this is just saying hello is of type string and it equals ARR, just like that. We have two ways of assigning values, either using brackets or using the equal sign, all right? A length function is there to find the length of a string. So if it's a type string and we put dot, we will see different methods or functions. One of them is the length that return the integer that says it's a type integer, and here's the length variable. It stores how many bytes, the length, number of bytes, all right? Concatenation of a string is done by concat. And here's the concat function. When we say dot concat, provide by string, or just using the plus operator. So if this is hello and space, of course, comma space, and this is world, and we say another string equals the first plus the second, this is concatenation. All right. Below, fragmented code also does the same job. Then we append the first, append the second. We add So we have the append method that does concatenation. All right. All these are string methods. A single character at specific index in a string can be extracted by calling char@. Method. Extracting a single character by using this method, char@. Below code will print W to the output string. So we say, so we define a string of called text. This is the variable name is text, and we store initial value hello world. Then text 7 is the W, because this is 1, 2, 3, 4, 5, 6, 7, 8. But start with 0, so the W is the 7 in the array. All right. So compare first. First equal first, then prints. All right. First compare first. So the first is hello. Okay, so all these together from here all the way to here, right? So the first is hello. First, this is the first. All right. Remember that string is an object, so if we call equal to compare two strings, it will compare the memory location of the strings. If both string objects are not pointing to the same memory location, same string, then it will fail. But many times we want to compare if the contents of the two is the same. So string class has provided equals method. So we have a method called equals. So the equal method, this one, string class, will compare if the given string content is the same as the string object on whose equal method is called. Method equals with S equals is case sensitive, just like C++ language. It's all case sensitive. It will consider the uppercase and lowercase characters different. The below code will give true if str is compared with str2, but at the same time it will return false if str1 is compared with str3. So 1 is hello, all lowercase. 2 is hello, also all lowercase. 3, the first letter is uppercase. All right, and here is the comparison. Here it will return 1 or true. Here it will return false because it's case sensitive. String height. This is the output. This one is the output. All right. String matching. Every word processing program has a search function. Any editor, in fact, any type of editor, simple or advanced, they have a find or search. Sometimes they have find and replace, right? In which you can search all occurrences of any particular word in a long text file. For this, we need string matching algorithms. So we are talking about the algorithms used to search a string, or string matching algorithms, all right? One of the is the brute force search, that you go through every single byte. We have a pattern that we want to search in a text. The pattern is of length m, and the text of length mn, where m is of course less than n. The brute force search algorithm will check pattern at all possible values of I in the text, where the value of I ranges from 0 to n minus m. The pattern is compared with the text character by character from left to right. When mismatch is detected, then pattern is compared, shifting the compared window by one character. And here's how to do it. brute force search, and the arrays are vectors, right? Brute force search. All right, and here we have, all right, worst case time complexity is a function of m times n. This is the worst case. The best case is a function of m. The average is a function of n. This is the time complexity, all right? And that was the first one, the brute force. The second one is Robin-Karp algorithms. Robin-Karp text search algorithm or text matching algorithm is somewhat similar to the brute force algorithm because the patterns compared to each text box. Instead of a pattern at each position, a hash code is compared. Only one comparison is performed. The hash code is a pattern compared with the hash code of the text window. We try to keep the hash code as unique as possible. The two features of a good hash code are collision should be excluded as much as possible. The hash code of a text must be calculated in constant time. A collision occurs when hash code matches, but the pattern does not. All right, and we have multiplication by 2 the same as left shift operation, multiplication by m to the power of m minus 1. All right, we want this multiple times, so just store it in a variable power m. We do not want to do big multiplication operations, so modular operation with a prime number is used. All right, and here is the Robin-Karp implementation. And here's the remaining part. And now we go to the Knuth, Morris, Pratt, Knuth, or I don't think the K is pronounced, Knuth, I don't know. Knuth, Morris, Pratt algorithm. After a shift of the pattern, the brute force algorithm forgetting all the information about the previous matched symbol. This is because of which its worst case time complexity. The Knuth-Morris-Pratt algorithm make use of this information that is compared in the previous comparison. It never recompare the whole text. So this is the trick. The algorithm never recompares. All right. So now we have 3 different algorithms: the brute force and Robin-Karp, and the third one is the Knuth-Morris-Pratt. All right. So in this Knuth-Morris-Pratt pre-processing step is required. We try to find the border of the pattern at different prefix of the pattern. A prefix is a string that comes at the start of a string. Proper prefix is a prefix that is not the complete string. Its length is less than the length of a string. Suffix is that comes at the end of a string. Proper suffix is a suffix that is not the complete string. Its length is less than the length of a string. Border is a string that is both proper prefix and a proper suffix. So we need pre-processing step. All right. And this is called KMP, Knuth Morris Pratt preprocess, right? We have a loop outer. We have to loop outer loop for the text and inner loop for the pattern. Here's the text, here's the pattern. All right. And here is the details, how to implement it. Example, use the same KMP algorithm to find the number of occurrences of pattern in a text. And here's the solution. All right. Dictionary symbol table. So we finished 3 text search methods, algorithms, and we called it text matching algorithms. We have another one that's called dictionary symbol table. All right. A symbol table is mapping between string, which is the key, and a value that can be of any type. A value can be an integer, such as occurrence, account, dictionary meaning of the word, and so on. BST, binary search tree for strings. We covered that in previous chapters, and it's repeated here as a binary topic. We talked about this as a tree topic. All right. Binary search tree, BST, is the simplest way to implement symbol table. Simple str compare function, str compare, string compare, can be used to compare two strings. If all the keys are random, the tree is balanced. Then an average key lookup can be done in logarithmic time complexity, logarithm of the n, number of elements. And here's the implementation, string tree. And here's more about the implementation. And here's more. All right. And now we have the hash table. Also, this has been covered before. And here is just a quick repetition. A hash table is another data structure that can be used for symbol table implementation. Below hash table diagram, we can see the same name of that person is taken as a key, and their meaning is the value of the search. The key cannot be repeated, right? So the word cannot be repeated. The first key is converted into a hash code by passing it to appropriate hash function. Inside the hash function, the size of the hash table is also passed, which is used to find the actual index where values will be stored. Finally, the value, which is the meaning of the name, is stored in the hash table. So this is how to implement a dictionary, how to do a dictionary. We use hash table. All right. And here's the function. So the name, which is the key or the word, and its meaning is the other thing. A hash table has an excellent lookup of a constant time. Tree or trie, I'm not sure how to pronounce it, is a tree in which we store only one character at each node. This final key value And this has been covered in previous chapter when we talked about how Google suggests words while typing. It uses the same idea, right? This final key value pair is stored in the leaves. Each node has R children, one for each possible character. For simplicity purpose, let's consider the character set is 26, just like English. Corresponds to different characters of English alphabets, or 28 in Arabic language, or something, or different character set in other languages, all right? Tree or trie is an efficient data structure. Using trie, we can search the key in a function of m, time. This is the time complexity, where m is the maximum string length. So it depends on what you are trying to search for. Trie is also suitable for solving partial match and range query problems. And here is the tree or trie search matching, and matches a character by character. Consumes a lot of space, but it's really quick. And here's the implementation. More about the implementation. And more about the implementation. And we are almost done. All right. Ternary search tree or ternary search tree. Tree or tries have a very good search performance, where m is the maximum size of the search string, but tries have a very high space requirements. All right, every node contains pointers to multiple nodes. Each pointer corresponds to possible characters of the key. To avoid this high space requirement, so to fix this shortage, to avoid this high space requirements in the regular tree, ternary search tree, TST, is used. TST, I think this also has been covered in one of the chapters, but we'll go through it real quick. A TST avoid a heavy space requirement of traditional tree while still keeping many of its advantages. In TST, each node contains a character and an and, sorry, not and, an and of the key indicator and 3 pointers. The 3 pointers are corresponding to the current car hold by the node, characters less than and characters greater than. All right, just like here. Ternary search tree. All right, TST, and here is the implementation. Problems in strings. Regular expression matching. Implement regular expression matching with support of this and asterisk special characters. This matches any single character. The star matches 0 or more of the preceding elements. And here is the example or a problem with this. Here's the solution of the problem. All right. Order matching, another problem. Given a long text string and a pattern string, find if the characters of the pattern string are in the same order in the text string, right? For example, the text string is this, and the pattern is this. Match, order matching. Here is the fix. Here is how to do it. All right, so we receive a pointer to the first array and a pointer to the second string array. And here we put the two integers. One is called iSource, the second is iPattern. And we store the size of the first one in the source length and the size of the second in the pattern length. Then we do a for counter from iSource equals 0. iSource is less than the source length, then iSource plus 1, 1, all right? And here we say source of this index, of this counter, if it equals to the pattern of this counter and starts with 0, then increases by 1, right? If this equals that, if the pattern equals this, return 1. Otherwise, return mismatch. This is how to find the match. ASCII to integer conversion, write a function that takes a character array and convert it to an integer. And we do this by ASCII to integer. So the character and the value, and return the value. And here's we are shifting. This greater than or smaller than twice, it does a shift, all right? To upper, write a function that will convert a lowercase into uppercase. So just if it's over 97, which is the start of the characters, and these are all lowercase, all right, then it will return them in the uppercase by going 32 bits. This is written by analyzing how the ASCII code is written, right? So you have to look at the ASCII code and write this, but it's written here and it's ready for us. This is the problem and this is the solution. And to lowercase, we just changed the minus to a plus here. Pretty much the same. The uppercase are these. In this range, it starts from 65, while the lowercase comes after it starts from 96. Yeah, just like this. It's also from the ASCII table. Unique characters. Write a function that will take a string as an input and return 1 if it contains all unique characters, else return 0 is a unique character. Just like that. All right. Permutation check. Write a function to check if two strings are permutation to each other's. Right. Here is the solution. These problems are really useful. It's something to try. Palindrome check. Given a string of an array, find if the string is a palindrome or not. Palindrome means it can be read from both directions, if I'm not mistaken. All right. Reverse case function. Write a function that will convert lowercase letter in a string to uppercase and uppercase to lowercase. So just flip them. So if it's uppercase, convert to lowercase. If it's lowercase, convert to uppercase. Just toggle, all right? All these functions can be seen in Word document. It does the toggle for us. All right, power function, right? A function that will calculate x to the power of n, taking x and n as arguments. And of course, we use the PO, so we have to include the CMath library. String compare functions, strcmp, string compare. All right. And here's the implementation. Reverse the characters of a string, reverse string. All right, and here's the implementation to how reverse strings. And the reverse word, reverse the order of words in a string sentence. So we just reverse the order of words, and here's how to do that. Print anagram. Given a string as character array, print all the anagram of the string. Anagram. All right. Here is how to do it. Shovel string. Write a program to convert array A, B, C, D, E, whatever, into A1, B2, C3. Just shovel them. All right. That can be done just like that. Binary addition. Given two binary strings, find the sum of these two binary strings. So binary addition, we add them in a binary form. Here's how to do it. And at the end of this chapter, which is the string chapter, it's all related to strings, which is really nice. We have these exercises. All right. We have these exercises. And these are more exercises. And way more. And in the next chapter, we'll talk about algorithm design techniques.